Okay, so here we have another circuit here. It's another first order circuit. We have an inductor here. This time we're trying to find this voltage V0. Now, as we're going to do for every problem in this chapter, we're going to start out by writing down that V0 of t is K1 plus K2 e to the negative t over tau. So every single problem in this whole chapter, when we're solving these, we're going to start by that and figure out the three constants K1, K2, and tau. And in order to find those, we're going to look at the circuit at three different points in time. The first point in time we're going to look at the circuit is at right before 0, right when the switch is about to change. And so if I draw my circuit here, the switch has not opened yet. I have my 12 volt source, my 2 ohm resistor, another 2 ohm resistor. Oops. We have a 4 volt source upside down here, 2 henries, and this is 2 ohms. However, the only thing I want to point out is that since the switch has been this way for a long time, we've reached steady state, and in steady state, inductors are shorts. So again, steady state, if you have an inductor, it goes to a short, and if you have a capacitor, it goes to an open. And so if I look at this here, what I want to do is I want to find the current through the inductor at this point in time. And again, the reason why we're looking for that and not the final answer V0 is because the only thing that we know that's going to stay the same over instantaneous changes is either current through inductor or the voltage through capacitor. So let's go ahead and solve this maybe by node voltage here. Call this V. So then I would have V minus 12 over 2 plus V plus 4 over 2 plus V minus 2 over 0, or V minus 0 over 2. See. Okay. So we'll go ahead and clear out the denominators here, and we'll have 3V equals 8, or V equals 8/3. And once we have that, then IL of 0 would be 8/3 over 2, or 4/3 amps. That gives me the initial voltage here, initial current, I should say. Okay, that's the first time you look at it. The next time we'll look at it is right after the switch changes, and when that happens, this middle circuit here doesn't actually matter anymore because it's not going to be connected. We do have the inductor now because it's no longer steady state, something has changed. And we need to find our R Thevenin with respect to that inductor. And in that case, these two resistors are going to be in series, so we're going to have 4 ohms. And then I have to tell you the other formula here, that the tau is going to be L over R when you have an inductor. And so that would be 2 henries over 4 ohms, or 0.5 seconds. That gives you your tau for this one. And then we can go ahead and find the initial value here. So we want to find the V0 of 0 plus. Well, we know that my IL of 0 is 4/3 amps, which then means we know that V0 of 0 plus is 8/3 volts. Now I do want to point out that in this particular case, the V0 before the switch happened and the V0 after the switch happened actually were both 8/3 volts. But that's more of a coincidence actually. It's not guaranteed to happen, and you really need to either look for voltage across capacitor or current through inductor. Just want to remind you of that. Anyways, getting back to the problem now, the third time period we'll always look at is as infinity. And when you have infinity here, it's going to go back to being in steady state. And steady state means that we are going to lose the inductor. So the inductor becomes a short. And so we can find that V0 of infinity here by current voltage divider is 6 volts. And that's always going to be your K1. So V0t is 6 plus K2 e to the negative t over 0.5. And in order to find K2, we plug in 0. It has 6 plus K2 equals 8/3. Remember where we got that from. And so then that means K2 is 8/3 minus 6. That's 8/3 minus 18/3 is negative 10/3. And so my final answer then is V0 of t is 6 minus 10/3 e to the negative t over 0.5. And my units are in volts. Again, it's a lot to take in at first, but through repetition, you'll see the general process here.